Okay, so for this one, we have to find the formula for IFT. So first thing, let's get the Laplace for all of these. Actually, let's do that later. So for now, this is what we're gonna do. We're gonna draw the circuit for when t is less than 0. So we just ignore this the voltage source here. So it'll look something like this. So we have I of t for when t is less than 0 passing through here. Then we have I of O here. This is the resistance and this is the inductance. We're assuming it'll look like this for a long time, so obviously this short circuits. And pretty much I of t should be equal to your I_O. So, and since current passing through an inductor can change instantaneously when we flip the switch to the other uh, pivot B, that means the second t is equal to 0, it's still equal to I of O. So our initial condition is equal to I of O. Now let's focus on the circuit when t is greater than 0. So we have the following. We're going to assume that this is a circuit when t is exactly equal to 0, okay? So right now the inductor doesn't short circuit. Alright, so what we're going to do is find the find the Laplace transformation for all of these. So this will just be VO over S because it's being times by 1, so Laplace of 1 is 1 over S. Laplace of resistance is just R. And now this is the interesting part. So recall, voltage is V of t is equal to the inductance times di of t over dt. Getting the Laplace for this, we have V of S is equal to L times S of I of S minus I of 0. Okay? And our initial condition is equal to I of O. Okay? So we would put I of O here. And since our initial condition isn't 0, this is what we're going to do. So we can't just write SL and call it a day. We have to go a little further. So for this portion of the circuit, we can either do one of two things. We can add a voltage source like this, or we can add a current source like this. So our voltage source, what it's going to be equal to, so first we have to expand this, so it'll be SLI of S minus IO of L, and this value will be your voltage source, I mean. If I said current source, I meant voltage source. And if you wanted to go through this route instead, where you use a current source, you pretty much have to isolate for this I of S. So it'll be V of S plus IO of L all over SL is equal to I of S. Break this up. So this and this cancels out. So the current source would be IO of S. Okay? So we would pretty much replace these two ports with either one of these two. It's up to you which one you want to work with. But let's work with this one because we could just do one mesh and be over with. So what we'll do is include this and then include a voltage source. It's going to be IOL, and the inductor here is just going to be SL. Okay, so now we can just do a quick mesh. Let's call this mesh I of S. So I of S, it enters from the negative port of VO of S plus I R. I'm going to call I of S just I plus ISL minus IOL. Okay, now we're going to factor out this I. So VO of S minus VO of S minus IO of L is equal to 0. Okay, so next thing, we're going to bring both of these to the other side. So it'll just be equal to VO of S plus IO of L. Divide everything by R plus SL. Okay, so what we're going to do is we're going to factor out an L, the inductance. So we're going to factor out an L from here. So it'll be R over L plus S plus L times R over L plus S. And these two should cancel each other out. And look at this. R over L, that's time constant, tau. If you remember we would do first order circuits, R over L is time constant. So what we can do is replace R over L with tau, and same goes for here. So tau plus S. Okay, and this is equal to I. So now we just have to find the inverse Laplace of all of this. So the inverse Laplace of I of S is just equal to I of t. The inverse Laplace of this should be easy. If I'm not mistaken, it should be, since IO is like an initial condition, I believe it should be the following. We just do IO, then 1 over tau S, or S plus tau. Oh yeah, sorry, inverse Laplace I mean. And this can be represented by the following. And we can just do e to the power of minus tau times t. Okay? And now for this one, to get the inverse Laplace, we will first have to do partial fractions, because it's SL times tau plus S. So SL, I'll do S plus tau instead. And this will be equal to, I'm going to bring this L up here. I'm going to do VO over L instead. There, so that way this looks more neat. So it'll be A over S plus B over S plus tau. Okay, so times everything by S times S plus tau. So we get VO over L is equal to A times S plus tau plus B times S. So when S is equal to minus tau, B will be equal to VO over L times minus tau. So it'll just be the following. And recall tau is equal to R over L. So if you put R over L here, these two L's cancel out. So it'll be minus VO over R. And when S is equal to 0, our A is equal to VO all over L times tau. And tau is R over L. So it'll just be VO over R. So this will pretty much be VO over R over S plus minus VO over R all over S plus tau. And getting the inverse Laplace of these, inverse Laplace of 1 over S, that's just 1, so it'll just be VO over R. And this we can represent this as the following. And the inverse Laplace of the inverse Laplace of 1 over S minus tau, that's e to the power of minus tau times t. So it'll just be e to the power of minus tau times t. And then we add this to it because we're doing two inverse Laplaces. So we'll do plus IO times e to the power of minus tau times t. We can add these two together. So it'll just be IO minus VO over R times e to the power of minus tau times t plus VO over R. And this will be equal to your I of t. And this is for when t is greater than or equal to 0.